Hey everybody. Today I'm going to show you how to calculate just about any discrete probability using R. R comes with 4 built-in functions for all the major discrete probability distributions, including the binomial, geometric, negative binomial, hypergeometric, Poisson, the list goes on. The format for the commands is always the same, which is incredibly helpful. Probability mass functions, PMFs, start with the letter D. Cumulative functions start with the letter P for probability. Inverse CDFs start with the letter Q for quantile. And to generate random values from the distribution, the function is going to start with the letter R. Additionally, the rest of the function name is always the same shortened version of the distribution name. Here's a table summarizing the commands for the biggest 5 distributions that you tend to run into. For instance, to compute in the binomial distribution, the probability mass function is d binom. The cumulative distribution function, the CDF, is p binom. The inverse CDF is q binom. And to generate random values from that distribution, you use r binom. The rightmost column in this table is giving you the math for the probability mass function, just so that you can make sure to match these up correctly. Let's do a couple of examples. Suppose we have a random variable x that has a binomial distribution with parameters n equals 12 and p equals 0.3. So we're doing 12 Bernoulli trials with a 30% chance of success on each one. I want to compute some probabilities, then find a percentile, and then generate some random values. And I want to do all of this using R. Let's start with those probabilities. When we want to calculate the probability that x equals 4, we're looking at a probability mass function. So we're using d binom. We feed it the value of interest, 4, and then the parameters in order, n and p, 12, and 0.3. In this case, we get about 23.1%. Similarly, for the probability that x is less than or equal to 4, we're looking at a cumulative probability question. It's a p binom. We pass it the value of interest, x equals 4, and then the 2 parameters in exactly the same order to get about 72.4%. To do the probability that x is greater than or equal to 4, we're going to do 1 minus the probability that it's less than or equal to 3. Because in this binomial distribution, which has support that consists only of the integers between 0 and 12, the events x greater than or equal to 4 and x less than or equal to 3 are complementary. 1 minus p binom, 3, 12, 0.3, we get about 50.7%. Next, let's find the 80th percentile in this distribution. And that means the smallest value in the support, so we're going to need one of those integers, that has cumulative probability greater than 80%. And the notation for that is pi sub 0.80. We do this with a q binom, which is the inverse CDF. We feed it the percentage of interest as a decimal, so 0.80, and then the same parameters in the same order. We get back the number 5. And we can confirm that that's the right answer using the CDF, using p binom. P binom of 5, 12, 0.3 is about 88%, while p binom of 4, 12, 0.3 is only about 72%. So in order to have a cumulative probability of at least 80%, we have to have a value of x equals 5. Now, all of these functions that we've been talking about are vectorized, and that means you can compute multiple probabilities or multiple quantiles at once. So, for instance, we can find all of the cumulative probabilities for this distribution with the command p binom 0:12, which gives back all of the integers from 0 to 12 inclusive, 12, 0.3. And you can see that these cumulative probabilities start very near 0 and go all the way up to 1. Finally, let's generate those 100 values from this distribution. And we do that with the r binom command. This time we specify the number of values that we want to have randomly generated, so 100. The parameters are the same as always, 12 and 0.3. In this case, the values I get range from 0 to 8, and the average of those 100 values is 3.64. The expected value of this distribution, by the way, n times p, 12 times 0.3, is about 3.6. So in this case, the actual average of these 100 values came out very close to the expected value. Incidentally, you may have noticed that command set.seed of 0 there. That's resetting R's pseudo-random number generator. So if you're going to try and replicate my results, if you want to do that exactly, you should include that command. Otherwise, you'll just get different random values. Here's another example. Every day, a new author has a 10% chance of selling a copy of their new ebook. Assume that purchases are independent of one another and that there are never multiple sales in a single day. So here I'm basically saying, assume we have Bernoulli trials. Find the probability that the first purchase occurs on the 10th day, and then find the probability that the second purchase occurs during the second week. And so that means on days 8, 9, 10, 11, 12, 13, or 14. Let's let x be the number of days that passed before the first purchase, and y be the total number of days before the second. X has a geometric distribution, and y has a negative binomial. In each case, the parameter p is going to be equal to 0.10 because there's a 10% chance of a sale on any given day. Now, you have to be really careful when dealing with the negative binomial and geometric distributions because they're two different PDFs and therefore two different PMFs, and so you kind of have to be aware of them. Typically, when I'm talking about these distributions, I'm talking about the total number of trials needed. When you're using R is referring to the total number of failures that occur before the last success. Now, it's not too hard to translate back and forth between the two because the total number of trials is the number of failures plus the number of successes, but you definitely have to keep an eye out for which one you're talking about and translate back and forth as needed. With the convention of talking about the number of trials before the success, we're trying to find the probability that x is 9 in the geometric distribution with parameter p equals 0.10, because if the first sale happens on the 10th day, then there were 9 days that were failures before that. And then we need to compute the probability that y is between 6 and 12 inclusive, because that means the total number of days, including the day of the sale, is going to be between 8 and 14 inclusive. Y, by the way, in this case has the negative binomial distribution with parameter r equals 12, we need 2 successes, and p again, 0.10. So we compute these probabilities using commands in R. The first one is a probability mass function question, so we're using dgeo. We feed it the value of interest, 9, and then the parameter p, 0.10, and we get about 0.039. So the probability that exactly 9 days elapse before the first sale, which will be on day 10, is about 4%. Secondly, the probability that y is between 6 and 12 inclusive is pn binom of 12, 2, 0.10 minus pn binom 5, 2, 0.10. So I'm taking the probability that y is less than or equal to 12 and then subtracting off the probability that y is less than or equal to 5. To leave only the probabilities that y is between 6 and 12 inclusive. Again, because we're having a discrete distribution here, we have to be careful about when we include the endpoints in this interval. Overall, we get about 26.6%. So that's the probability that the second sale occurs in the second